So one more poll. Please answer this question. Most of the time, for what software do you create meshes or plan to create meshes? This will help us design future capabilities of Griddle, knowing what type of software you use. And if your software is not specified here, feel free to send us email to let us know if you would like to have support for such software. You can send email on Griddle to Griddle support, basically Griddle at itascacg.com. All right, I think we can stop the poll now. And let me see if I can actually share the results of the poll. This is the first time I'm using this webinar, so let me see if I can find the right button to share the results. Okay. You probably can see the results right now. Interestingly, a lot of people using it for Flag 3D, a little bit less for 3DEC, a little bit less for finite element software. All right, well, let's proceed with the presentation. Thank you for your responses. So, general improvements in Griddle. So first of all, for those people who worked with Griddle 1.0, you probably remember how I cannot say difficult, but maybe cumbersome was to install Griddle. Initial first version of Griddle was, I would say, somewhat experimental, and the main attention was given to meshing capabilities rather than to usability capabilities such as installer or updating capabilities. So with this version, we significantly improved the installer. Now the process is very simple. Basically, you just download the installer. As long as you have Rhino 6 or Rhino 7 installed on your machine, you can just click on Griddle installer, and within a few moments, it will install on the system and fully integrate within Rhino system and Rhino 6 or Rhino 7, or both, if you have both installed. So the process is very simple. Also, Griddle automatically will remove all previous versions of Griddle 1.0 from the system. There's a little bit more information about it in user manual. So if you're interested in Griddle and you install it, please refer to user manual for additional details. We also implemented additional automatic check for updates. And because of new installer, you can easily update Griddle. You just install new version of Griddle. So if an update for Griddle is available, shortly after you close Rhino, you will see a pop-up window that will notify you that an update is available. It will look like this. You just click on this link, follow, which will open Griddle update page in your default browser. You just download the new version of Griddle and install it, and you will get new version. So with this, of course, we're planning to periodically release updates to make improvements, provide new features, which was not possible for previous version of Griddle. And now it works similar to all other Itasca software. So we also revised and improved embedded documentation within Rhino help pane. You will see this later on some examples. We improved consistency in output file naming and better project management. We improved consistency in security logic. If you remember, for those users of Griddle 1.0, you may remember that Block Ranger had somewhat different security options than the rest of the plugins. Now it's all uniform security logic, and Griddle now accepts only Griddle license, no other licenses. And besides, we significantly redeveloped and added a lot of new material in user manual and tutorial examples. And here I would like to briefly show how they look like. So if you open Windows Start menu and just navigate to Itasca Griddle 2.0, you will have these options here. You may open Griddle manual or tutorial examples or tutorial files. It basically just will open a folder where all the tutorial files are. So let me show you. If I open tutorial examples, you can see it's a simple PDF. You can actually download it from Griddle webpage without even installing Griddle itself. And there are a lot of useful examples. For example, let me just show the last one, which is rather realistic model of large open pit mine with multiple intersecting faults. So you start with some rough draft model, and there are instructions, step-by-step instructions how to work with it. And at the end, you will end up with FLAG 3D model containing, I actually don't remember, but something in the range of maybe 100,000 or a few 100,000 zones with intersecting faults, so with which you can continue working. So feel free to explore user manual and tutorial examples. And let me switch to the next slide. So a bit more detailed information about improvements in structured meshing. As I mentioned, Griddle contains really only one tool for structured meshing, which is Block Ranger, even though it's a rather powerful tool, but it operates on slightly different principles than all other Griddle tools. Block Ranger is a structured hexahedral volume measure that operates directly on 4, 5, or 6-sided solids represented by BREP objects or boundary representation objects. Essentially, this could be tetrahedrons, objects topologically equivalent to tetrahedrons, prisms, or pyramids, and hexahedrons. And Block Ranger directly creates volume meshes by discretizing such solids. So what was improved in Block Ranger, it's the following things. Now Block Ranger is able to handle concave solids. Here's an example. Previously, Block Ranger within Griddle 1.0 would fail meshing such geometry. Overall meshing engine is a bit more robust. If let's say you supply the geometry that has internal connectivity issues, which may not be directly visible to user, the mesher will try to fix it before proceeding with meshing. Block Ranger also has an option to create boundary surface meshes from solids volume meshes, like you can see here. This is a new feature. It's somewhat experimental right now, and it can be optimized, but it already proves how powerful this idea is when creating hybrid meshes. I would recommend everybody to watch this webinar of how to create a hybrid mesh by combining Block Ranger and other Griddle tools. This webinar is based on using Griddle 1.0. With Griddle 2.0, these operations would be easier because we can directly create meshes, boundary meshes within Rhino. And I will have a demo example later about creating hybrid mesh. And additionally, we have some more output formats such as FLAG 3D binary, FreeDEC, 7 text and binary, and CSV. With CSV, you can analyze data output within Excel or maybe imported it into MATLAB. FreeDEC 7, it's a new grid format that can be loaded in FreeDEC 7, and it's much faster than FreeDEC version 5.2. This format is very similar to FLAG 3D format. Very small demo about Block Ranger that I would like to share with you. So here we have a model. It's actually a model of some shaft with a tunnel going through it, and it's a small part of rather huge model of excavation. I believe it was for a subway station. And you can see that this model consists of a number of different solids that's in full contact, which are in full contact with each other. Previously, Block Ranger wouldn't be able to handle such solids because there's a lot of concave solids here. Now, if I would like to mesh it, I can click on Block Ranger icon. And by the way, this is the Griddle toolbar. That's what you will see when you install Griddle. I just drag it to the side for convenience. And I'll go to mesh settings. I will change some items, some parameters here. And by the way, here's that Rhino embedded help. You can see when I clicked on Block Ranger, you can see that if help pane is open, you will get all the information about specific command and different options in this command. So it can be useful for novice users. Well, let's proceed with meshing. I'll also select Generate Surface Meshes. And in a few moments, we're going to see how the surface meshes look like. Let's save the file. This is volume output. Let me select polysurfaces and delete them. We just now have meshes. You can see that everything is meshed properly. And each mesh corresponds to a separate solid block. You can see that these meshes essentially represent what's on the boundary of volume mesh. So this is an example of Block Ranger, and later we will have one more example of creating hybrid mesh where Block Ranger will be used with unstructured volume measure. So let's switch back to the presentation. And now let's talk about improvements in unstructured meshing tools. As I mentioned, there are 3 different unstructured meshing tools, which are Surface Mesh Intersector, Gint, Unstructured Surface Mesh Remesher, GSurf, and Unstructured Hex Dominant or Hexahedral Dominant Volume Mesher. They are grouped here in this box, I would say, within the Griddle toolbar. And these tools are typically used in such workflow to create volume meshes. So essentially, when people start with Rhino surfaces, solids, or initial Rhino meshes, these meshes need to be remeshed, need to be intersected to make them conformal. Conformal means that all neighboring faces fully share nodes and edges. There's no so-called attach. There would be no so-called attach conditions. Then, when meshes are made conformal, they can be remeshed to achieve desired mesh parameters such as density, element quality, and so on. And finally, when we have proper surface meshes, watertight surface meshes, we can create volume mesh, either tetrahedral or hex dominant, using GVol, and that volume mesh would be unstructured. So essentially, this workflow is presented in these images. We start with initial mesh, then we'll do intersection of meshes, then we'll do remeshing, and if we create watertight domain, this volume mesh can be created for watertight domain. About improvements in these tools, Surface Mesh Intersector received several improvements. First of all, it's the ability to keep meshes either merged or separate after the operation. If you used Griddle 1.0, you probably remember that after doing surface mesh intersection, you will get one fully merged mesh, and that mesh would lose all the mesh attributes such as name, color, and so on. Now, if meshes are kept separate, all the attributes are preserved. You can clearly see it here. And also there's additional option to split intersected faces and put them into separate layers. There will be a demo example about this. With regard to surface mesh remesher, GSurf, first of all, we have a faster and more robust engine. We keep, same as in Gint, we can keep meshes merged or separate after the operation. If meshes are separated, then all the attributes of the meshes are preserved. There are more meshing controls, such as gradation of element size along the mesh, weight on quadrilaterals, shape quality optimization, and you can read about these parameters in the help, embedded help, or in the manual. We also allow to specify local mesh size in the URL field of the mesh. URL field initially, of course, is used for different purposes, but we utilize it to specify mesh size for simplicity. And this is done to preserve mesh names. And finally, there's improvements and improvements in the logic for hard edges and nodes and local mesh size. All right. another little demo about GINT, surface mesh intersector. Here you can see number of meshes. They have been obtained from a rather large model. Let me show you this model. This is a model of open pit mine with number of intersecting faults, and there's a discrete fracture network between a couple of the faults. The model is very huge. There's actually more than 800 meshes here, and I don't even show the domain in general. And number of planar faces or surface faces is close to 2 million in this particular model. So, but this is a really real model which was analyzed by Itasca engineers and was successful. The results were successfully obtained. But let's first look at this piece of the model. So we have piece of DFN and two faults, and the idea is to decouple this DFN from the faults to prevent the interaction between these meshes. It's actually not obvious how to do this, but Griddle provides several tools how to do this, and I'll show you just one of the ways how to do this. So let's first try to intersect these faults and DFN using some tolerance. Please note that in advanced parameters now we have output mesh either separated or merged. Merged would correspond to how Griddle 1.0 worked. We will keep it in separated, and we will split intersected faces, which will put them in separate layers. So let's intersect them. And you see that all the intersected faces have been put in sub-layers of each of the layers, like DFN set. And let's select these objects. You can clearly see that with this intersection tolerance, just few faces were intersected. And this is not enough to make all the meshes conformal or even to separate the faces. So let's undo the separation and try to use much larger tolerance to for sure intersect everything and separate intersected faces. What we get now is that not only proper faces were intersected, but some faces within the meshes itself were intersected, which is undesired. So for this particular model, it's actually rather challenging to find proper tolerance, intersection tolerance. So there's another way how to approach this situation. So I undid the whole operation again. And what I'm going to do now, I'm going to slightly extend DFN meshes. So they for sure, you can see they already slightly protrude or intersect the faults, but not completely. So I'm going to extend the DFN meshes so they for sure intersect the fault meshes. I will describe later in more details how this works, but for now, just follow me on this. So you see now all the meshes, all the DFN meshes protrude through the faults. I can remesh the internal meshes, the DFN meshes. To make them more uniform. So the remesher is done, and now I can intersect everything using even zero tolerance. And now you can see that all the faces that I wanted to be intersected and separated are there, and I can just easily delete them. Now all the DFN, as you can see, there's a gap between DFN and faults. Now all the DFN meshes are separated, and they not going to interact with the faults when volume mesh is created. So this is one example showing how GINT works. The next example, brief example, is about GSurf. Here we have some topographic surface, and let's say we would like to piece of topographic surface. It comes from another big model, real engineering model, and let's say we would like to remesh everything with specific parameters. We would like to have central mesh very fine, while other meshes rather coarse. So if we use standard parameters for GSurf, we would specify some some limits for edge length of elements. the result would look like this. Now we would like to refine this central part. So this can be done in specifying local mesh size. And let me show you how that can be easily done without losing the name of the model. Let's say the name of the mesh. The name of the middle mesh is middle. And I would specify here element size, desired element size. And let's say I would like to specify 0.2. It's in meters, and please refer to the Griddle manual to understand how element size is measured. And for the bottom mesh, I will specify slightly larger element size. Now, if I remesh everything again, you can see central mesh is much finer. All meshes are conformal. And this mesh is coarser. And you can see that element size changes gradually from fine to coarse. And this gradation can be easily managed by going to advanced parameters and specifying max gradation. So if you want, you can even download demo version of Griddle and play with this parameter, even though there are some limitations, but you would be able to get the idea. All right, that's all for this example. And let me switch to the next slide. So in unstructured volume measure, GVOL, we implemented faster and more robust engine. We got more meshing controls similar to surface remeasure GSurf. Also, we implemented automatic check for surface mesh problems before volume meshing. You would see a pop-up message notifying you if there's any naked edges, which can be indication of holes, or clashing faces, which can be indication of non-conformal faces or overlapping faces. So if you have very complex model, it will give you an idea that there might be potential problems in the model before volume meshing. There are also several new output formats, FreeDEX7 rigid or deformable, and text and binary formats, and CSV. So a couple of words about rigid and deformable formats for FreeDEX7, which are new formats. If you use FreeDEX7 rigid format, each volume element becomes a rigid block. So if you input such model into FreeDEC, you will see a picture like this, where each zone is essentially a rigid block. To work with such model, you would typically have to join or merge zones together to form much bigger blocks. Or you can pick FreeDEX7 deformable format, and on the output you will get this type of result, where each block would be much larger and would be separated by joins over here or over here or over here, and each block would contain deformable zones. It's much faster to load such models within FreeDEC and work with them in FreeDEC. And we also got more detailed logs. These images show how volume meshing parameters can affect the volume mesh. Specifically, here, this is some excavation shaft in some big domain. Here, we would like to change the gradation of elements in the volume mesh. And by changing some parameters such as gradation, target size, and different parameters, you can get somewhat different image, somewhat different results with more gradual change of volume elements. There will be a couple examples that will involve volume meshing, and you will see how it works. So now let me talk about new and improved meshing utilities. There are quite a lot of new things in Griddle, new utilities to work with surface meshes. They are grouped here, and I will mention a few of them. For example, new utilities mesh healing tools, Gheal. When Itasca engineers worked on real projects, they often see that the data that we received from other engineers or field data are often very imperfect, containing a lot of problems. And it takes a lot of time to really clean the model and prepare it for meshing or remeshing. And Gheal can assist with that. It can automatically fix a number of issues. Another tool that we have, it's mesh extraction tool. It received many more sub-options. Previously, it had only single surface extraction. Now we can extract all surfaces, which is equivalent somewhat to exploding meshes. We can extract boundary faces, non-manifold faces, and surfaces within solids, like shown here. There's also a new tool, mesh extension tools. There are three options here. You can see that you can extend boundary or a piece of boundary along tangential direction of the boundary or faces attached to the boundary. And another new tool is mesh extrusion, which you can use to quickly create watertight domains for modeling. And the last two tools, non-manifold extract and colorize objects, are the same as in Griddle 1.0. So now there are several demo examples I would like to show, and first we will start with mesh and utilities demo. So here's first example. This is actually an example from Griddle tutorial, the last example, open pit mine. I slightly modified it just for this presentation and to simplify it. And here you can see two faults that intersect, and they intersect with open pit. And these meshes are completely valid. They are fully conformal. So if we had a watertight domain around it, we could produce volume mesh out of these meshes. But here we would like to do something different. Let's say we would like to separate pink and green mesh to prevent their interaction in the numerical model. So we can simply do that by extracting the boundary faces of the pink mesh. You see, when I extracted boundary faces, they got highlighted in different color. I can select them and can simply delete them. And there's a gap now between two meshes. So this is one way to do it. Let me undo it and show another way. So let's merge green and pink meshes. I'm just gonna join them to get single mesh. Now this is single non-manifold mesh because there are basically three faces connected along the intersection edge. And that's why I can extract non-manifold faces. You can see when I extract them, I got these faces here, and I can easily delete them. I got now a gap, much bigger gap, that separates both faults. But this is still a single mesh. So now I would like to explode it to make two different faults out of it. So I can explode it just by using the highest possible break angle. So that means that break angle will not be accounted for. So now I got three separate meshes, and I will assign this mesh back to fault 2. Furthermore, if I would like to densify mesh along the intersection with the pit, I can do the following thing. Let's join all the meshes again. Now again, we got a single non-manifold mesh. I'm gonna extract non-manifold faces. You see they got extracted, they got highlighted in different color, and I'm gonna specify different element size. Let's say I'm gonna specify element size 3 meters. Now I'm gonna remesh everything with the following parameters. Let me see my notes. I will specify higher gradation, and I will keep meshes merged. So the operation takes a little bit of time, and we can see that there's significant densification along the intersection. Let me explode all the meshes again and delete the top parts. There are a few little pieces left. And now I will reassign layers back to initial. It's not a pit, it's fault 1 and fault 2. So at the end, I got non-interacting faults and densification along the intersection with the surface mesh. If I create a watertight domain around this model, I can create a volume mesh out of this model. There's one other example I would like to show here with regard to mesh extension, free extend tool, but unfortunately, I think I'm going to be running out of time, so I probably will have to skip this example for now. If you have time later, or if you have questions later, I can show you this free extend tool. So for now, let me just hide this example, and I will switch to other examples. I will show this direct shear test example and creating hybrid mesh, but unfortunately, looks like I'll have to skip one other example as we're going to be running out of time. So with regard to direct shear test, it's a very interesting example. Again, it's a real model that came to us and with which we worked. So we can see a single surface mesh here that unfortunately has lots of problems, and that these problems are not really visible. This surface mesh comes from a point cloud, and this point cloud represents electronic microscopy image of rock surface. So essentially, this mesh was obtained from a point cloud, which was initially triangulated, remeshed multiple times, and now this mesh contains problems, which need to be fixed before working with it. So this tool GHeal allows to visualize these problems. So in pink, you can see all naked edges, which depict holes or borders of the meshes. And in red, you can see non-conformal, overlapping or folding faces. You can see here, like there's a problem with this face. So to work with this mesh, let's try to fix it. First, let's try to intersect it with some tolerance to try to remove non-conformal faces. And we can see by showing errors again that there are no more red curves, but there are still problems. So let's try to fix the mesh in automatic mode. And you can see that there are a number of options here, what exactly to fix. And let's select all of them for now. So the fixing looks good. There are no more internal problems. All the problems were fixed automatically, but there is still a piece of crack left here that we would like to kind of fill up with faces. First of all, to do this, let's try to remesh the whole mesh to make it a bit more uniform. So let's try to remesh it. With these parameters. Oh, sorry, I mistyped it here. We got a bit more uniform mesh, but unfortunately this mesh contains some new problems now. If I check for problems now, we can see that there's some extra face that appeared here, and there's something happening over here. So let me zoom to this area. You can see that this area is actually a ridge, and the face is on the other side of this ridge. It's this extra face that's not connected to anything. And there's also this extra little volume here. So let me actually remove this first, this volume by removing faces. And now let's try to fix this mesh again using GHeal. I'm gonna use automatic heal, but this time I'm not gonna select all options. I'm gonna select only those options that are needed, which is mend cracks and remove protrusions. When I fix it, we can see that this mesh is good now. So I can hide these layers, these two layers that show errors, and I can create a solid domain out of, or watertight domain out of it. So first of all, I created two planes to which I'm going to extrude this mesh. And I'm gonna use these parameters here. This is G-extrude option in Griddle. And you can see I created watertight bottom domain. Now let's do the same with top domain. And here I created top domain. Now I can assign these meshes into different layers. Let's say this is going to be our top mesh, top box, and bottom box. So we got full model in less than 5 minutes. And if we hide one of these domains, we can see that there's in between it's our surface. Now we can easily create 3D model by volume meshing. Let's select 3D 7 and deformable formats. So we get only 2 blocks here. And we're gonna save it. The process is rather quick, as you can see. And now if we load this model into Griddle, into 3D, loading it is rather quick as well. And here's our 3D model with the joint inside that depicts our surface. So this is example about G-Hill. And I'm going to show quickly this creating hybrid mesh example, and we'll finish with one other example about DFN. So let me show you the hybrid example. Again, this is example from the manual, from Griddle tutorials. And I'll show you how to quickly create hybrid mesh for this example. Here we have a tunnel split into stages, excavation stages. We have topographic surface and some kind of fault here. So let's first work with the tunnel. We need to create structured mesh for the tunnel. So let's use Block Ranger. We'll use standard settings, but we will create surface mesh. It takes maybe about 30 seconds for this particular model to create volume mesh and surface mesh. And I will save volume mesh in FLAC3D format. So surface mesh creation is a little bit slow because it has to be created separately for each of these solids. But we're gonna get there soon. So now we're saving the volume mesh, and here's surface mesh. So let's now select the surface mesh and put it into separate layer. Let's call it tunnel mesh. And I'll put it into tunnel mesh layer. Now we can hide the tunnel itself. So here we got surface mesh corresponding to volume mesh of the tunnel. What I need now is to extract the external surface of this tunnel mesh. And I'm gonna do this by using extracting all surfaces with break angle 80 degrees. So now I have separate pieces of this surface mesh. And I'm gonna select all the internal pieces and delete them with a select small command. You can see that I selected only the internal pieces. And now we got the mesh. I'm gonna join it. We got single. I'm gonna change the color, and we got this single mesh now. And I'm gonna switch to shaded view. Also, I'm gonna fix the normals just for better look. Okay, here we got our mesh. That's what we're gonna work with. And I will need to create a copy of this objects for later. Now let's quickly work with topography and default. Let's create watertight domain. I'm gonna go to the whole view, and I'm gonna create a plane, bounding plane for domain extrusion. And I'm gonna put it a little bit down here. And I'm gonna basically extrude the topographic surface to that plane. Let me see the parameters. And here's our domain. And now we can see that basically fault is partially intersecting this domain. The tunnel is intersecting, but we need to extend the fault for full intersection. So what we're gonna do, we're gonna extend all boundaries by 10 meters, and the fault now is fully intersecting the domain. Now we can intersect the whole model using intersector, volume, surface mesh intersector. And we can remove external parts. And the same for these cups. Now I'm also going to remove this version of the tunnel, as we need to remesh only the domain and the fault. And we got basically two holes. So please note that there are these edges that represent the hard edges of the tunnel, and they're going to be used during the remeshing process. So I'm going to remesh the whole thing with quad dominant mesh, and these parameters. Remeshing is very fast. Now I can remove hard edges, and here we got our tunnel and unstructured mesh around it, and you can see that they fully conformal. Now I can create volume mesh. I will use hexahedral dominant mesh and FLAG3D binary format. Meshing takes probably 20 seconds, 15 seconds. And at the end, I will get volume mesh for the exterior of the tunnel, and it's going to be unstructured mesh, while the interior of the tunnel is structured mesh. Basically, when this meshing is done, I can load both meshes into FLAG3D, and that's what I will get. Structured mesh within the tunnel and unstructured mesh outside the tunnel. And you can see that it's fully conformal. There's no attach conditions are needed. And you can see that it's nice, pretty much hexahedral mesh. All right, I'm kind of running a little bit out of time. I'm going to switch to the last example and briefly show it, and we'll finish with the presentation. So the last example is about using Griddle in scripting and development in general. So Rhino offers extensive developing tools for creating scripts and plugins. Among them are Grasshopper, which is visual programming language, Rhino Script, which is based on VB Script, Visual Basic, Rhino Python based on Iron Python, and two lower-level languages or SDKs that are, one of them is C# SDK, which is based on .NET framework, and C++ SDK. Griddle commands can be called from any of these programming languages and development environments. And I'm briefly going to show you a Python script that was written to create a discrete fracture network. So here we have a tunnel. This example is going to take probably a couple of minutes only. Here we have a tunnel, and we'll create a DFN around it and a domain automatically within Python script. So this Python script is over here. It's rather simple script, even though it may seem a little bit hard, but for novice user. But essentially, the whole script, the main portion of the script is here. All other functions, all these functions are to prepare the model to create DFN, essentially disks. But this part of the script calls Griddle commands. You can see here that it calls gsurf, gint, then gsurf again, then it calls gextract, and finally gwall. Even though DFN is typically created or often created for FreeDEC, this time I created it for FLAG3D just because it's easier to, or it's faster to load larger files within FLAG3D. So let me run this script and you'll see what's happening. And by the way, this can be done in the loop, so I can create tons of different variations of DFN. For now, I'm just going to run single example. So let me run it, and you will see. You can see that Rhino automatically creates all the disks or planes, automatically meshes everything, remeshes, and in about 20 seconds, it will complete with volume meshing. So while it's doing this, let me, now it's extracting meshes within the tunnel, and it will remove them. And it's now doing volume meshing automatically. And we're done. So if we look at what happened here, I'll switch to shaded view. The script automatically created these two domains. The internal domain is DFN, external domain is kind of empty, but they fully connected. Let me delete these external domains, and you can see how DFN looks like. That's how DFN looks like. It's created randomly within, there's actually 3 predominant deep and strike angles in which this DFN is created, but each plane is created randomly according to Gaussian distribution that was programmed within the script. So now if I load this in Flag 3D, you can see the progress bar here. It's going to be pretty fast. So this model contains around 130,000 zones, and that's my DFN. You can see how it looks inside. All the meshes are fully conformal. There's no attach conditions. This is tetrahedral mesh, but of course you can create hex dominant mesh if needed, even though for free deck, it has to be a tetrahedral mesh. So with this, I would like to finish with demo examples and conclude the presentation with the last slide. What's coming next in Griddle? First of all, we will probably be working on web licensing, and we'll try to deliver it with one of the updates, future updates. Then for the next version of Griddle, we may consider developing new functionalities involving related to boundary, background, and anisotropic meshing. We will probably consider functionality to mesh closed volumes individually within Rhino, not the whole model at once. We will try to improve visualization or create new tools to visualize volume meshes or some specific elements or groups of elements within Rhino, let's say bed elements. So you can quickly analyze the resulting volume mesh. We will consider working on improvements in grouping logic. We will try to do tighter integration between structured and unstructured mesh, and maybe creating new tools such as gheal, gextract, and so on. Providing more capabilities for finite element output. As I mentioned, right now it's rather basic, but we definitely will try to do more improvements in the output. And finally, we will do more optimization and multi-threading. So with this, I would like to finish the presentation. Hopefully it wasn't too much information, but hopefully it was rather useful for you. A recording of this webinar will be available shortly. And if you had any questions, we will try to answer them now. You can also type them in the question box. And I will try to answer them. So thank you for your attention. So Dave, let's see if we got any questions, any specific questions from people.
Hi, Andre. So far we have one question, and the question is, what is the difference between structured and unstructured meshes?
Structured mesh essentially is a mesh that follows regular topology or regular geometry. That means that you can even map structured mesh into IJ space and basically find elements by index I, index J. Unstructured mesh doesn't follow any specific topology. Elements essentially, if you try to map it to some regular space, IJ space, let's say, they would be located at random positions. So Block Ranger, it's our structured measure, and GWall, it's unstructured measure. And you have a choice which one to use depending on the input geometry. However, Block Ranger operates not on meshes, but rather on solids, while GWall operates on surface meshes. So that's where the difference is. And if you have more questions, of course, you can send us email or please refer to Griddle website and also Griddle manual, which you can download directly from the website, even without installing Griddle itself. You can download it from here, Griddle manual. It's just a PDF. And there's a bit more explanation of what's the difference and even some examples. So hopefully that answers your question.
Okay, great. Thank you. So we have some feedback. I've been working with Griddle for a while now, and would be happy to get some feedback. Is there a feature in Block Ranger that is similar to size ratio of FLAC3D?
I would say yes and no. It's you can create size ratio by adding additional edges or so-called hard edges in Block Ranger. This is just a second. This is described in the manual, I believe, and it should be described even within the built-in help of Block Ranger. Let me see. If I go here to help, and at the bottom, yeah, it's briefly described here. You can create. Well, sorry, this is about creating local size. It's not the ratio. Sorry, I was wrong. So probably right now there is no size ratio. You can create. You can change local size of the block during discretization, but not create a gradation in Block Ranger. So this is something we probably should work on. I guess this rarely came up to attention, and thank you for bringing it up. We'll try to work on it and maybe even provide an update for Block Ranger with this feature.
Okay. And the same person had a suggestion. Another useful feature would be automatic rounding of sharp corners. So
I would like to ask here rounding of sharp corners of surface meshes or polysurfaces, because this would be two different things. And I would say actually Rhino 7 provides tools to rounding sharp corners of polysurfaces through using sub-D objects, which can be meshed later.
Well, they just specified automatic rounding of sharp corner functions that split the solid into corresponding volumes.
Could you say it again, please?
Another useful feature would be automatic rounding of sharp corner function that splits the solids into corresponding volumes.
Well, it's not quite clear to me, but if the person who asked this could send an email to us, we can have a discussion and maybe come up with some useful feature in Griddle. So
good. We have that the person logged, so we can get back to them on that.
All right, sounds good. Here's my email. You can send directly to me, or you can send it to Griddle support at griddle@itascacg.com. All right, anything more? Any other questions?
Anisotropic meshing becomes very important in many cases. It would be good to see it added to Griddle. A question of gradation. Can volume structured meshes do gradation?
First of all, with regard to anisotropic meshes, it's in our plan. We at least going to do it initially for surface meshes, unstructured surface meshes. Structured meshing with Block Ranger kind of already has this by specifying local mesh size, as I showed let me see, within this help system. Essentially, by specifying local mesh size along specific edge, it can create an isotropic mesh, to a certain degree, an isotropic mesh. And there was a second part of the question. Sorry, I already forgot it.
It was gradation. Can volume structured meshes do gradation?
Yeah, so Block Ranger right now doesn't have gradation. That's what I kind of answered earlier. You can specify local mesh size to, let's say, densify mesh along this edge or in this direction, essentially, this discretization direction, which will make it anisotropic, but it would be uniform gradation. So this is something we will need to work on.
Okay. Next question. Are there improvements for deposit geometries to analyze dynamically? I remember that meshes built with Griddle version 1 derive in results in very small dynamic time steps and very large analysis times.
So essentially, for dynamic analysis, of course, you will need to have larger elements. And that's larger elements and also nicer shape elements. That's where these different parameters would come into play, meshing parameters, let's say gradation, optimization, shape quality, and so on, for surface meshing and for volume meshing. These parameters cannot guarantee that you would, let's say, increase dynamic time step to a specific level, but they can help you achieve or at least get closer to what's needed by manipulating the size and quality of output meshes. And that's why it's important to visualize these meshes and maybe visualize specific elements, let's say tiniest elements or bed shape elements within Rhino, so you can play with different parameters and quickly decide on which parameters to pick. So this is something we will plan to do in future version of Griddle or maybe in some updates. For now, basically, you have to play with parameters, load your model into modeling software and analyze it there to see if the elements are what you need.
Okay. What are the advantages of hexahedrons when compared to tetrahedron elements?
Well, specifically in FLAG3D, hexahedral elements provide much more accurate numerical modeling results. This is because hexahedral elements within FLAG3D contain several overlays. Essentially, it becomes equivalent to higher order elements in finite element analysis. Tetrahedral elements in FLAG3D are linear tetrahedral elements with no overlays, no internal kind of internal stress strain averaging. So they would be equivalent to very basic tetrahedral finite element elements. For FLAG3D, it's very important to have as many hexahedrals or prisms or even pyramids, because you would get just a much more accurate results than if you work with solely tetrahedrons. FreeDeck is a little bit different because FreeDeck operates with blocks of tetrahedrons. And even though tetrahedrons can only linearly deform, but the block itself, within the blocks itself are rigid, and there's a separate level of interaction between the blocks. So it's a little bit different story. So just to conclude, for FreeDeck, tetrahedrons are pretty much okay. For FLAG3D, it is better to get hexahedral dominant mesh for majority of cases. Even though I would like to mention that in FLAG3D, there is an option to split tetrahedrons into, I believe it would be 4 hexahedrals. I believe it's a zone split command, and you will get denser mesh, but it's going to be pure hexahedral mesh. That's what a lot of people use. They initially create purely tetrahedral mesh, load it into FLAG3D, and then split every tetrahedral element into 4 hexahedrons, just to get much more accurate results. And for finite element, again, as I mentioned, we have rather basic capabilities for finite element. Griddle outputs all linear elements. Depending on the type of element, you may get different effects of finite element modeling.
A person is asking if it's possible to do the example of the structured and unstructured meshes in Rhino 6. So what perhaps we could do, Andre, is if you wanted to do the examples that were skipped over after the webinar, we can simply include those in the video of the webinar that will be distributed afterwards.
Well, the example that was skipped over, it's not very critical, and it's not related to hybrid mesh. I don't think you would really need to see it. Essentially, this example is outlined in Griddle tutorial examples, and Griddle tutorial examples contains an example of hybrid mesh. So you can just download the tutorial. There's an example creating a mixed structured and unstructured mesh. And it's essentially the example that I showed. It just goes step by step, starting from this geometry. It's a little bit rougher geometry. I mean, initially rougher geometry, and it shows step by step how to create everything. At the end, you will end up with pretty much the same result as I showed. There's also an example that I skipped right now on meshing a model with analytical surfaces, where the model is defined by these analytical surfaces, and it describes what kind of problems you would have if you try to mesh it directly, kind of more or less brute force approach, mesh it, and then try to create volume mesh, and you will see that there would be a number of problems. So it shows an alternative way how to work with this type of analytical surfaces and create unstructured mesh for them. At the end, you would end up with something like this. So that's the type of example that I skipped right now.
Okay, great. There's a question. So yes, there will be a recorded version of the webinar available to see on YouTube and through our website. So next question, can we say that the surface is adequately, one second. Can we say that if the surface is adequately meshed, the mesh for the volume will also be correct and appropriate?
If the surface is adequately meshed and it composes watertight domain or number of watertight domains, then you basically always will be able to create volume mesh out of it. And one other thing that I kind of didn't show, didn't have time for it. Let me just show a very simple example. Let me create mesh box. Simple mesh, just a box. This mesh is, of course, suitable for volume meshing. But let's say I remove a face out of it. Just one face. There's a hole in this mesh. And of course, if you have enormous model, you may not see that there's a problem in it and this face would be missing. So volume mesher now automatically can analyze that there might be a problem, and it will show this message to you that surface meshes contain naked edges or clashing faces, and it highlights them. You can see that there's a problem now. However, it will show such message, let's say if there's internal surface that kind of floats within this domain. That surface such surface may contain naked edges, and this mesh will be shown as well. So you have to be kind of discreet about this message, and if you see it, maybe go back and analyze what's happening, if that's really a problem or that's by design. And you can turn off this message by going here into advanced settings and just say, I don't want to see this message anymore. And now you can try to create volume mesh, but you see volume mesher complains now that it was not able to create volume mesh. So if you have a rather large model, sometimes it takes, may take even up to hours, couple hours to create volume mesh. And let's say there's a problem with a single phase somewhere. So instead of waiting for multiple hours to volume mesh to complete meshing, you may see initially that there's a problem if you enable that message. Or you can analyze this type of model with ghill and indicate errors. You can see as well that there's a problem here. Essentially, you can hide this and just see that there's something happening with the model that requires fixing.
Okay, great. Just a couple more questions left. When using Rhino Python, how do you choose surface meshes you want to improve?
Well, you can select different objects. You can find them by name, by layer, by type. There's enormous amount of help available for Rhino. Let me actually open again Rhino Python script. And you can see I even put a few links to myself to remember. So let's open. No, I think it's this one, this first link that this is a description of Rhino Python, what it is. And yeah, this is the page, Rhino Python page. You can read a lot of stuff about how to use Python within Rhino. There's a number of examples here, how to work with different geometries, how to call different commands. You can, as I mentioned in my presentation, you can even call over here lower level commands, such as those commands that implemented specifically in C# SDK, can be invoked from Rhino Python. So you can really create rather complex models using Python. You can completely automate your process using any of these tools. Actually, here's an example of a well bore with perforations that was automatically created by well, it wasn't Python script, it was C++ code. But it just started from a set of numerical parameters that specify, for example, well bore diameter, perforations diameter, location of different faults, and so on. Initially, there was no model or anything, just few numerical parameters. And the code automatically created this type of model and meshed it and produced volume mesh. So I would really recommend you to look into Rhino website, specifically this one, Rhino Python. If you need more information, please send us email, and I will be happy to share all this information with you and even provide maybe a few tips of how to use Griddle commands within different scripts. And also there's a lot of information on GitHub, a lot of different scripts, Python, C++, C#, Rhino script, Grasshopper scripts. So essentially you can just copy a number of routines and functions. Actually, these three functions here I directly copied from GitHub. They just select objects in different layers or find objects in layers. They trim objects, create Rhino mesh. So this is, I only wrote like this, well, technically these 5 functions, which is probably like 150 lines of code. So hopefully this answers your question.
Okay. Next question. There's just a couple left. I am not too familiar with Rhino, but does the 3D model have to be solid, 3D mesh, 3D surface, or 3D poly prior to meshing using Griddle?
So as I mentioned, there are 2 types of volume measures. Block Ranger operates on analytical solids. It's essentially polysurfaces combined together. So structured volume measure block ranger requires analytical surfaces or polysurfaces, and they have to be watertight. Unstructured volume measure, GVol, operates on surface meshes. Essentially, surface meshes have to create a watertight domain, like you see here. It's let me undo this. You see, this is a watertight domain created out of essentially 6 perpendicular meshes. Its equivalent, analytical equivalent, would be a box, which is analytical equivalent. And if we click here, we can see this is, well, it's called closed extrusion, but essentially it's a polysurface. I can explode it in number of surfaces. And you can see these are just surfaces defined by boundary representation, essentially by the edges and curvatures between edges. Now, meshes are discrete representation of surfaces or polysurfaces. And Rhino doesn't even have option to explode meshes, but Griddle provides this option. I can explode them here. And you can see that this mesh essentially consists of, or this closed domain consists of 6 meshes. So block ranger would operate, let me undo everything, just to get back. Block ranger would operate on solids like this, and GVol, unstructured surface meshes, would operate on watertight domains composed of meshes.
And of course, you can go from polylines to surfaces to meshes.
Yeah, absolutely.
Mesh.
So, for example, here I can create initial triangulate or create initial mesh. This is a standard Rhino operation. The Rhino mesh that it created is rather coarse. It just created like 2 triangles here and quadrilateral here, but then I can remesh it with whatever parameters I want. Let's say something like this with surface remesher, and now we got another surface mesh. So basically, you can always go from analytical surfaces like surfaces or polysurfaces represented by any form, any object, BREP, NURBS, or sub-D. You can create meshes out of them and then use Griddle tools to work with those meshes. Or if you want to have structured mesh, you can directly work on polysurfaces or solids represented by BREP objects. But opposite is not possible. You cannot, well, technically you can create analytical objects by approximating surface meshes, because surface mesh is essentially a discrete representation of some surface. I hope it was somewhat clear, but if you have any more questions or would like to have discussion, you can send me email or send email to Griddle support, and we will try to help you understand the difference of all these shapes and how to work with different shapes. And overall, these are all standard shapes within CAD software, between CAD software. Other CAD software have similar type of shapes, or similar type of objects, I should say.
Great. Okay, and the last question is Block Ranger able to solve the intersection of complex tunnels, several complex tunnels?
No, it automatically, in automatic mode, it doesn't split intersection of complex tunnels. You can do this manually. It's not very complicated process conceptually, but it may be a little bit of labor intensive. This is something, again, we need to consider about improving. I would like to refer you to this presentation. Let me see where it is. Oh, I think I missed it. Oh, no, here it is. So over here, if you go to itascacg.com, learnings webinars, and type and look for this presentation, it shows an example of how these intersections can be created. You can also just type in search in YouTube, on YouTube about this presentation. But overall, Griddle doesn't do this intersections automatically. You would have to prepare intersections manually. Then when tunnels are properly split into shapes that Griddle Block Ranger supports, you can basically select all of these shapes and mesh them all at once automatically. And actually, you should do that to create conformal meshes, volume meshes. So, but overall, we definitely need to and plan to work on improvements in Block Ranger, specifically with regard to this functionality.
Great. Well, that's the end of the questions. So thank you very much, Andre, for your presentation. We will post a video of the webinar in the next few days, and we will send a link to everyone who's registered for the webinar. It will also be available on our website and our YouTube channel.
All right, sounds great. Well, thank you everyone again for attending. And as I mentioned before, if you have any further questions or suggestions about what improvements you would like to see in Griddle, feel free to send email again directly to me. And I forgot to put here email of Griddle support, which is very simple. I believe it's griddle@itascacg.com. I'm pretty sure you can find it on our website as well. So feel free to send us email, and we will try to help you as much as we could, as much as we're able to. So thank you for your attention, and hope that you will find using a new version of Griddle easy and productive for your work.
Great. This concludes the webinar. Have a good day, everybody. Bye-bye.